Hi, thanks for visiting our poster. Here, we're displaying our progress towards strongly correlated 2D system of dipolar sodium cesium molecules. First of all, why do we care about sodium cesium? Sodium cesium molecules feature a large dipole moment of 4.6 dBi, and they are an ideal platform to create strongly interacting dipolar many-body systems. Here we show the apparatus for producing the results that we will present today. Our setup consists of an optically plugged quadruple trap and a cross ODT in the horizontal plane. Additionally, a reservoir beam is used to increase the trap volume. In the ODT, the trap frequencies of cesium and sodium are similar. We create sodium and cesium condensates simultaneously by utilizing sodium as the coolant for cesium in the two-stage sympathetic cooling. The first stage is RF-induced evaporative cooling in the magnetic trap. The second stage is the evaporative cooling in the cross ODT. The typical number of BEC are shown in the poster. We investigate the cross formalization of the mixture. On the formalization curves, we can obtain the interspecies scattering length at both 23 and 894 Gauss. We then calculate the mixability condition to be approximately 5 at 23 Gauss and 3.3 at 894 Gauss, which is above the threshold of 1. We then observe the formalization mediated by the thermal contact between mixable and overlapping clouds. Our dipole trap model also shows that sodium and cesium BEC overlap with each other. We also observed that sodium BEC extends the lifetime of the cesium BEC by a factor of 10. We conclude that overlapping BECs of sodium and cesium are mixable, and they can be utilized to create break-cold sodium cesium ensemble. Here we show our result of making sodium cesium molecules. We associate a molecule with sodium and cesium at fast power resonance. Typically, we have 20,000 molecules with lifetime of 20 milliseconds. We then do the dissociation measurement to determine the value of the interspecies resonance at 864.12 Gauss, which is in excellent agreement with the data in the reference. To further characterize the resonance, we do the RF spectroscopy to measure the molecular binding energies. And the coupled channel calculations fit to the measurement to obtain the parameters of the resonance. We thank Professor Eberhard Thiemann for the theoretical calculations. We apply the time of flight measurement to determine the molecular temperature. We release the molecule from the trap and then dissociate them. Then we measure the cesium temperature at different ramp speeds. Different ramp speeds add different kinetic energy, and we extrapolate to the 0 ramp speed to get molecular temperature. With this technique, we can optimize the molecular temperature. We are able to create the coldest molecular ensembles out of the dual BECs. The temperature can be turned from 1 microkelvin to 18 nanokelvin, and the cloud size ranges from 20,000 to 600. We also achieved a unity phase space density of molecules. Now, we saw our recent progress toward ground-state molecules. We implement the single photon spectroscopy of sodium cesium molecules to locate a suitable intermediate state for stirrup. Here, we show the spectrum of Cp sigma plus omega equals 1, V equals 26 state, which agrees with the data reported in the reference. Currently, we are working on the stirrup. Here you can see the scheme and the laser system. Last week, we successfully implemented the outlet tiles spectroscopy. At this point, we are getting very close to the ground-state molecules and are looking forward to exploring strongly correlated systems in 2D in the near future. Now, I would like to thank our group members, our undergraduates, and the funding agencies. We are happy to have discussions with you during the poster session. Thank you.